Today we're going to be taking a look at how to find the volume of a three-dimensional shape. There's several different methods for doing this. We're going to focus on just the disk method in this video. Alright, we will be using the definite integral to find the volume of this three-dimensional shape. But before we get to that part and before we get to the actual formulas, I want to do some clarifying on why this works and how this works and the different things that we're going to be looking at. Alright, so in this diagram right here we have a curve, alright, and it's between x equals a and x equals b. Alright, so we're just looking at this blue region right here. If I revolve that around the x-axis, we are going to end up with this blue shape over here. It will be our three-dimensional shape that we're going to want to find the volume of. I'm going to focus on a representative rectangle. That's going to be what we focus on in the formula in a little bit. Okay, now if you take the representative rectangle and it touches the axis of revolution and it goes up to the curve, alright, the shape, come over here and look at this, the shape, when that representative rectangle is revolved around the x-axis, you get a disk. It forms a representative disk. Alright, one representative disk. Now the distance from the x-axis up to the curve, that ends up being the radius of that disk. All the way across would be the diameter, this would be the radius. So later in the video when I'm referring to the radius, alright, this is what I'm talking about, the radius of the disk, that representative disk that gets revolved around. Alright, now we are just going to take a look at one representative rectangle, alright, but we're going to use the definite integral, alright, to do this. That's going to be our formula. If you remember a Riemann sum, alright, we would take the rectangles and we would add them up, and then later you found out that the integral does give you the area under the curve. Alright, as you let the number of rectangles approach infinity, we're going to do that same thing here. We're going to focus on one representative rectangle. However, as we let the number of representative disks, I said rectangle a minute ago, representative disk approach infinity, alright, we will get to the volume of that disk. Alright, so we're going to focus on one. We're letting it approach infinity, the number of disks approach infinity. That's where the definite integral comes into play, and that's going to give us the volume of this three-dimensional shape. Okay, so just some background information before we start working it out. Okay, now here what I've done is we've laid out all the formulas. Okay, we're going to focus on first a function that is given to me in terms of x. Alright, so my volume is going to be equal to pi times the integral from a to b of f of x squared dx. Okay, now this is what my picture is going on. Let's say my curve is f of x here. I'm revolving around the x-axis. Alright, I'm going to focus on that representative rectangle. Alright, it touches the x-axis, it goes up, it touches the curve. It will have a width of delta x. Alright, I am integrating from a to b. Everything is in terms of x. My function is in terms of x. This is the formula I'm going to be using. Now, this f of x, alright, it is the distance from the x-axis to the curve. Alright, well, if you remember the picture of that disk being revolved around, that's the radius. So a lot of times this formula will be written in such a way as people will go volume equals pi times the integral from a to b, and then they will say it's the radius squared, and then dx. Alright, so if you want to think of it as the radius, I need this distance. Alright, well, the way I'm going to get this distance is f of x. From here to here, if I plug a number in, that will give me that distance right there. Okay, now over here, this is just rewritten in terms of y. If my function's in terms of y, alright, then I would still, the formula still remains the same, pi times the integral from a to b of f of y squared, and then dy. Alright, so here's my curve, but this time I'm revolving around the y-axis. Alright, my limits of integration are going to come from the y-axis, from a to b. My representative rectangle would be drawn horizontally, and I need the distance from the y-axis out to the curve. Alright, that would be the radius, alright, or f of y, okay, and then the formula says we square that. Alright, the width of that representative rectangle would be delta y. All right. The one main thing you need to remember with disk method is your representative rectangle is perpendicular to the axis of revolution. All right. So on this first example here, we were revolving around the x-axis, and my representative rectangle is perpendicular to it. On this example, my axis of revolution was the y-axis, and my representative rectangle is perpendicular to that. Okay. The other main part for disk method is that your representative rectangle touches that axis of revolution. All right, there's no gap there. That it is touching the axis of revolution. All right, that way you know you're going to be forming a disk when that revolves around. It will be touching. All right, now let's take a look at an example. All right, we'll work through three examples. Kind of three different scenarios, one in terms of x, one in terms of y, and then one revolving around something that's not one of the axes. Alright, so in this first example here we've got find the volume of the solid generated by revolving the region bounded by y equals x squared and the x-axis on the interval from -2 to 3 about the x-axis. Alright, so I would highly recommend sketching this out so that you know what you are looking at here. So that's what I'm going to do first. We're going to sketch. Alright, important parts in this. They gave me the curve, y equals x squared. It's bounded by that curve, and it's bounded by the x-axis, and it's bounded on that interval from -2 to 3. Alright, and the other important part is here, you've got to know which axis you're going around. So we're going about the x-axis. Alright, so I'm going to go ahead and indicate that so I don't forget that we're going around my x-axis right there. Alright, this curve, x squared, it's going to go through the vertex, and it's just a nice little parabola. So I don't have to be really accurate when I draw this at all. Okay. Now it's bounded between the x-axis, and I'm going from -2 to 3. So let's say -2 is right there. 3, let's say 3 is right there. Okay, so the region that I am focused on is going to be in here and then in here. Alright, now let's go ahead and place that representative rectangle on there. I'm revolving around the x-axis, and here's my curve that I'm working with. I know it's got to touch the axis of revolution and go up to my curve. Alright, so kind of wide there, but we get the idea. Alright, there's my representative rectangle. Alright, in other words, that is the radius of the disk. So the distance from here to here, that's going to be my radius of my disk f of x. Okay. Okay. Now let's set up our definite integral. Alright, let's use our formula. So the first thing I'm going to do is write down the formula from the other page. It was v equals pi times the integral from a to b of f of x squared dx. Alright, and if you want to think of this f of x being the radius, you can do that. Okay, the radius squared, the distance from the x-axis up to f of x. Okay, so as I begin to work this out, it's going to be pi times the integral of a to b. Alright, so -2 to 3, because it's got to come off my x-axis. Everything's in terms of x here. Alright, my function is x squared, so x squared, and the formula says to square that distance, and then dx. Okay, at that point, once you have the setup and everything's in there according to the formula, then this is just straight integration that it probably at this point you have been doing a long time. Simplify, integrate, and plug in your things. So we'll go ahead and work this one out. We may not work out the ones examples in the future, but we'll do this one. Pi times the integral from -2 to 3. Let's turn that into an x to the 4th dx. Alright, now if I integrate this, I'm going to have pi on the outside times a 1/5 x to the 5th, and I'll be integrating that from -2 to 3. Alright, plugging in the 3, we'll have 243 over 5, and then minus, plugging in a negative, that's going to give me a negative value, negative 32 over 5. And going ahead and plus and switching that out, I should end up with a 55 pi. Alright, usually I have my students leave things in terms of pi like that, so I've got a nice little 55 pi there. Alright, so that one pretty much was a straightforward example. Everything in terms of x, I was revolving around that x-axis. Okay, now let's do a second example. This time let's put the curve revolving around the y-axis. Okay, in this example, find the volume of the solid generated by revolving about the y-axis. The region in the first quadrant bounded by y equals x squared, the y-axis, and the line y equals 6. Okay, so let's go through there and find all of our important parts. We're still using this y equals x squared, but this time I'm going to be bounded by the y-axis and the line y equals 6. Alright, so I'm going to start by sketching. Okay, so I still have that parabola, but I only want in the first quadrant. It did say only in the first quadrant, so I only need to be focused here. Let's go ahead and label this y equals x squared. Okay, I am revolving around the y-axis. So let's put that on there so we don't forget. Okay, and then let's add that line y equals 6 on there. So let's just say if I come up there to 6. So if I add that, that's y equals 6. Alright, so I'm bounded by the y-axis, y equals 6 in this curve, so that means I'm focused on this area right in here. Alright, now let's put the representative rectangle on. Alright, I'm going to be revolving around the y-axis. Alright, so that means my representative rectangle has to touch my y-axis. So, representative rectangle. Alright, now, how wide that is, that's going to be a delta y. Okay, and you can think of this as being the radius of that disk, because as I revolve around that y-axis, this right here, the distance there, will be the radius of my disk, f of y. Okay, now something that you might want to consider here, we know we're revolving around our y-axis and everything. Our limits of integration have to come from this y-axis, and the other thing that you have to note, this equation is written in terms of x. We need to solve it for y because I've got to have everything in terms of y. If I'm going to go, my limits of integration are going to be from 0 to 6. Alright, that's off my y-axis. I'm revolving around this. My delta y is how wide that representative rectangle is. I've got to solve that equation for y. Okay, so let's go ahead and do that. Let's solve for y. Okay, so that's what I'm going to do. So I'm going to start out with y equals x squared. I'm going to take square root of both sides. Square root of y equals x. So in other words, I'm just going to go x equals square root of y. So this is that curve in terms of y now, which is what I need. Okay, so now let's set up our formula for our definite integral. Okay, so this one, v equals, it's still going to be pi times the integral from a to b. This time it'll be f of y because everything is in terms of y, that quantity squared, and then I'll have a dy at the end there. Alright, so for this particular one, v equals pi times the integral. Alright, we're going here's 0 and here's 6. We were up to 6, so from 0 to 6. Alright, the function in terms of y will be square root of y squared and then a dy. Alright, now at this point, like I said, you should be really proficient at integrating a definite integral and all that kind of stuff, so I don't want to take the time to do that in the video. You could pause the video, go ahead and work that out, and I do believe the answer should be 18 pi if you do that. So you could pause the video, work it out, and see if you can actually get 18 pi on that. Alright, now for the last example. Alright, in this last example, we're going to revolve around a line that is not an axis. That's a pretty common thing that happens a lot. They start you out revolving around either the x or the y-axis, and then they start taking you away from that. So in this example, it tells us to find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. Okay, so again, I'm going to want to draw a sketch of this so that I know what's going on. Okay, that's going to be an upside down parabola, and I've got y equals 1, so I'm going to need kind of a lot of room here. Alright, so let's take a look at important parts here. Okay, so f of x equals 2 minus x squared. Alright, and then I've got a g of x equals 1. And then about the line y equals 1. Alright, so I'm going to put this one on first. I know that it's shifted up 2, and it's going to be an upside down parabola. So I'm going to make that pretty high so I've got room to work here. Let's say this is 1. Let's say that's 2. Okay, so there is my f of x equals 2 minus x squared. Alright, my g of x equals 1. Okay, we said this was 1 because we said that was 2. This is 1. So my line, y equals 1. So this is g of x equals 1. Alright, but I'm also revolving around this y equals 1, so it really doesn't make any difference there. Alright, now I'm going to be revolving around that. So I'm going to put my little arrow on there to remind myself which way I'm going here. Alright, now if it's bounded by those two curves, that means I'm focusing on this area right in here. Okay, and my representative rectangle then is going to touch my axis of revolution and my curve, and everything is in terms of x here, so we're good. So there's going to be my representative rectangle. It'll have a delta x, how wide it is this way. Alright, and then keeping in mind that again is still going to be my radius. This distance will be my radius of my disk, because it'll revolve right around that, so my disk will be up there. Okay, and then we have additional things that we've got to find on this one. Okay, I don't know what that point is, and I don't know what that point is right there, but I'm going to have to do that for my limits of integration. So those are my points of intersection. I'm going to have to find my points of intersection. Alright, so let's see if we can squeeze that on right here. Points of intersection. Alright, that should be something that you should be able to do relatively easy. Hopefully you remember that all you have to do is set the two curves equal to each other. So 2 minus x squared, and I'm going to set that equal to 1. So I'm going to set those two curves equal to each other and then solve. So 2 minus x squared equals 1. Let's see, subtract 1 from both sides. So, and then move that x over to make it positive, probably that'd be good. 1 equals x squared, so x is equal to plus or minus 1. Okay, so this has got to be negative 1, this over here has got to be 1. Okay, so for those 2 points right there. Alright, now to get the distance of this radius, alright, this radius of my disk here, I got to get this distance. Okay, you're going to have to plug a number into f of x, because if I plug a number into f of x, that's going to give me the distance from here all the way up to the f of x curve. Alright, but that's too much. I don't need this right here, so then if I subtract whatever I would get when I plug a number into g of x, if I subtract this distance, so I've got this entire distance which is my top curve, all right, minus the distance to the bottom curve. All right, that would leave me with what is left right there. Okay, so let's put that in there. I'm going to run out of room here. So calculating my, let's do it in red. Calculating my radius of my disk. I need to take the distance to the top curve minus the distance from the bottom curve. All right, so I'm going to go top curve. I'm just going to write it that way, top curve minus bottom curve. All right, my top curve is my f of x, because that's the parabola. The bottom curve is the g of x curve. All right, so my f of x curve was 2 minus x squared. All right, minus my g of x curve is 1. Okay, so subtracting right there, I'm going to have a 1 minus x squared. All right, so that right there is my radius, the distance of my radius of my disk. The distance from here to here. All right, now I think I'm finally ready to set up my formula for finding the volume of this. Okay, so my formula, V equals, and I'm going to kind of rewrite the little formula here to instill what we did here. It's going to be pi times the integral from a to b. All right, of what did we do? Well, we found the radius of that disk, and we found it by doing f of x minus g of x. All right, now you don't necessarily want to memorize the quantity squared dx. You don't want to memorize f of x and g of x, because if they change the function names, all right, so it might be better for you to actually put in there top curve minus bottom curve. But you subtract the two curves there, that'll give you the distance of that radius, and then you square it. All right, so pi times the integral, we found our points of intersection, all right, as -1 and 1. All right, we did this already, we did the math right here, so the radius is going to be 1 minus x squared. I have to then square that quantity, dx. Okay, and then again here, hopefully you can calculate this integral out with too much problems. Probably what I would first do before I try to integrate this is I might FOIL it. So let's go ahead and do the FOIL step for you. Volume equals pi times the integral of -1 to 1. If we FOIL that out, we'd have a 1 minus a 2x squared plus an x to the 4th, and then dx. Alright, so foiling that out. From there, you should then be able to continue. You can hit pause on the video and then try to integrate that. Alright, if you do that and you get done, you should have a 16/15 pi as your final answer. Okay. Alright, so 3 examples of using the disk method for finding the volume. Alright, and kind of went from easy to medium to hard. Alright, lots of different things. As soon as you start revolving around something that is not one of the axes, then you've got a little bit more effort in finding that radius of that disk. Alright, but it shouldn't be too bad. Thanks for watching, and definitely share with your friends and give me a thumbs up. Thanks.